Hello everyone and welcome to this lesson. It will be a nice quick short video because we're just going to be covering one idea, but as with our previous number patterns, we've seen that we do get some more complex questions where we have variables instead of numbers in our pattern, and we need to be able to tackle these types of problems as well. So let's just jump straight into it. My first example, k plus 1, let me just make sure you see that's a 1, hey? K plus 1, k minus 1, 2k minus 5 are the first three terms of a geometric sequence. Calculate k and hence determine all possible sequences. So now what? Let's focus on what was important information that they gave us in this question. So they told us that the pattern is geometric. That's really important, because what do I know about geometric patterns? I know that there's a constant ratio where term 2 divided by term 1 is equal to term 3 divided by term 2. So maybe what I should do is, let me start subbing in term 1, term 2, term 3 into their relative places and see where we can go from there. All right, so let me just get rid of that. Term 2 is k minus 1. Term 1 is k plus 1 is equal to. Term 3 is 2k minus 5. Term 2 is k minus 1. And what we've done here is we've just created an equation where we need to solve for k, perhaps a more complex equation compared to the ones we did in arithmetic sequences, because we're working with the fractions, but that's not a problem. I'm going to, at this point, put brackets around my terms. Right, and you'll see why we're doing that now. Okay, so now we need to solve this equation. So I don't want to be working with fractions, right? So I need to get this out of the denominator and into the numerator, and same story over here. So we're going to use this very simple cross multiplication technique. You're literally just going to cross multiply like this over the equals to sign. So the denominator on the right hand side of the equation, you multiply up onto the numerator on the left hand side of the equation, and we do the same story on the right. So it's going to be k minus 1 times k minus 1 equals 2k minus 5 times k plus 1. And maybe now you're realizing why I introduced the brackets, because we are going to have to multiply a binomial times a binomial. Think of your FOIL, right? First outer, inner, last. Okay, so we're going to expand the two binomials, and then we're going to collect like terms. Okay, so let's see what this simplifies to. It's going to be k squared minus k, so that's going to be negative 2k, and then minus 1 times minus 1 is positive 1. On the right hand side, 2k times k, 2k squared plus 2k minus 5k, so we're going to have 2k squared plus 2k minus 5k will be minus 3k minus 5. Right, let's collect like terms. I'm going to collect them on the right-hand side of the quadratic equation because my leading coefficient will then be positive. The reason why I know to set up a quadratic equation is because of these terms squared. Right, it's not linear like in arithmetic sequence. We have a quadratic equation here, so we need to collect the terms. So we're going to have 2k squared minus k squared will be 1k squared. Negative 3k plus 2k, because now it's on the right hand side, will be negative k. Negative 5 is going to be minus 1 since it's now on the right-hand side. So negative 5 minus 1 is minus 6. And now we've got a really super basic trinomial to factorize here. So 0 is equal to k plus 2, k minus 3. Therefore, k is equal to negative 2 or k is equal to 3. All right, so we've calculated k. We've got two solutions for k, but we know we're expecting to get two solutions because we're solving a quadratic. But the follow-up question, hence determine all possible sequences. So this is saying we can potentially have more than one sequence happening here, which will be true since k has two separate values. So what we're going to do, we're going to substitute k equals minus 2 first and get solutions for that, and then we'll move on to when k is 3. So basically we've got two options. So the one sequence, I'm just going to put a 1, is when k equals negative 2. So term 1 in the first, right, term 1 is k plus 1. So now it's going to be negative 2 plus 1, which is negative 1. Right, term 2 is k minus 1. So k is negative 2 minus 1, which is negative 3. And term 3 is 2k. K is negative 2 minus 5. So that's minus 4 minus 5 minus 9. This looks good because, as you should be able to see, we're multiplying by 3 each time. So my constant ratio would be 3. So that pattern's looking good. The pattern would be minus 1, minus 3, minus 9. Okay, but we have another possible solution, right? If I look at k being equal to 3, right? If k is 3, then term 1 will be k plus 1, so 3 plus 1, which is 4. Term 2 would be k minus 1, so 3 minus 1, which would be 2. And term 3 would be 2k, remember k is equal to 3, minus 5, so that's 6 minus 5, which is 1. So this pattern, this is a very interesting pattern, don't you think? It's going 4, 2, 1. So before we finish up with this video, 4, 2, 1. Ask yourself, what are you constantly multiplying by to get to the next term? Because this is going to be a temptation. A lot of you may be looking at this and saying, oh, well, if I say 4 and I divide it by 2, 4 divided by 2 is 2. And if I say 2 divided by 2, 2 divided by 2 will give me 1. But remember, when I said a constant ratio, it's that you need to be multiplying by a specific value, not dividing. So if you are not if you're dividing by 2, what would you be multiplying by? Right? Remember that if you are dividing a value by 2, it's the same as multiplying that same value by a half. So be careful, because this isn't what you want to do, right? You want to be constant ratio is you are multiplying by a certain value. And let's do our test. Term 2 over term 1 is equal to term 3 over term 2. Right? So your constant ratio is a half. So we discovered a very important concept now, is that as tempting as it is in this instance to say let's divide by a certain value to get to the next consecutive term, geometric sequences is a constant ratio. We need to be multiplying to the next term. So if you start to see that your numbers are decreasing, right? If you say to yourself, well, if I'm dividing by 2, that's the same as flip the fraction over, change your sign. If you're dividing by 2, it's the same as multiplying by a half. All right, I mean switch my sign, meaning make your divide 8 times. Don't make your plus become a minus. Okay, so I hope that makes sense and that helps a bit. I think we must do one more example of this concept, and then we can practice ourselves. Okay, dokes, we're nearly there. Right, so second example. Let's go through this quick sticks. All right, so term 1 is x plus 2. Term 2 is 3x plus 1. Term 3 is 7x minus 1. All right, my question is, so these are the first 3 terms of a geometric sequence. Right, same question as before. Solve x and determine all possible sequences. Okay, so let's start off with obviously our very useful handy trick. Our term 2 over term 1 is equal to term 3 over term 2. Right, if you're solving for an unknown variable, we ideally obviously want to try and set up an equation so that we could solve for that variable. Because the pattern is geometric, that is why I'm using this trick over here. The term 2 over term 1 equals term 3 over term 2. All right, so term 2, remember that we use brackets. 3x plus 1 over term 1 is x plus 2. Term 3 is 7x minus 1 over 3x plus 1. Right, now let's just use that cross multiplication technique. So you're just going to multiply up and across like that. So you have 3x plus 1 times 3x plus 1 on the left-hand side of your equation, and 7x minus 1 multiplied by x plus 2 on the right-hand side. All right, now we're just going to expand the binomials and add up like terms. So it's going to be 9x squared plus 3x plus 3x will take me to positive 6x plus 1 equals 7x squared plus 14x minus 1x will be plus 13x minus 2. I'm going to collect the terms on the left-hand side of the equation since my leading coefficient will then be positive. So 9x squared minus 7x squared will be 2x squared. 6x minus 13x, that will be minus 7x. And 1 plus 2 will equal 3. All right, so I've just collected all the terms on the left-hand side. Let's factorize. Second sign is positive, so the signs are the same. They're both going to be negative. Right, so that'll be 2x squared minus 6x minus 1x. Take us to negative 7x plus 3. So therefore, x is a half, or x is equal to 3. Amazing. So now that we know what x is, we can figure out what the pattern will look like, what our sequence is going to be. So the first possible option is working when x is equal to a half. So term 1 is a half plus 2, because it's x plus 2. So that's 2.5, or 5 over 2. Term 2 would be 3x, so 3 times a half, which is 1.5 plus 1. So that's also going to be 5 over 2. And then term 3 Term 3 is 7 times a half minus 1. So that's 3.5 minus 1. That's also 2.5 or 5/2. All right. So I know this looks a bit weird, but you can see between the terms that we're just multiplying by 1. So a bit of a weird pattern, right? Our second option is when x is equal to 3. So with term 1, it's going to be x plus 2, so 3 plus 2, which is 5. Term 2 would be 3x, x is 3, so 3 times 3 plus 1, which is 10. And for term 3, it's going to be 7 times 3 minus 1. So 7 times 3 is 21, minus 1 is 20. Right, so that pattern looks a bit better. We can see that between the consecutive terms, 5 times 2 is 10. 10 times 2 is 20. So with a pattern like this, we're still going to get into talking about convergent and divergent series and delicious things like that. So we're not going to cover that right now. I just want you to get a basic idea of how we're going to approach and answer these questions if we get given them. All right, good job, everyone.